Welcome everyone to final video here on chapter 15, talking about chemical equilibrium. And in this video, we're going to talk about the Chateliers principle. Okay. So what is the Chateliers principle? Basically, it states, right, that if a system at equilibrium is disturbed by some change in temperature, pressure, concentration, right, if you change, right, how much products or reactants you have, okay, right, that system will shift, right, its equilibrium position to counteract the effect of that disturbance. Okay, and what it means by shift the equilibrium position, right, is basically it's going to form more products or form more reactants to counter this disturbance. Okay, because basically when you change the temperature, pressure, or the concentration of things at a reaction that's at equilibrium, often you're going to take it away from equilibrium. And every reaction wants to get back to equilibrium. So the reaction is then going to form more products or form more reactants, whatever it needs to do in order to reach chemical equilibrium. Okay? So, what is the effect of changing concentrations, right? So if I add a reactant to my chemical reaction, right? Let's done this reaction N2 plus 3H2 going to 2NH3, right? So if I add some reactants, right? What I've done is now I've added extra reactants to a reaction that was already at equilibrium. So what's going to happen is my reaction is going to want to use up some of those reactants and form products to regain chemical equilibrium. Okay, so the reaction is going to shift to the right and thus form more products in order to reach equilibrium. Okay, if I add a product, it's going to do the opposite, right? Now I've added some amount of products, right? Added something to the right side of my chemical reaction, okay? Added some stuff over here. That's going to cause the reaction to want to consume some of those products to form reactants in order to reach chemical equilibrium. And some reaction is going to shift to the left, right? It's going to go in the reverse direction and form more reactants, okay? Now, if I remove some amount of products, okay, right, then what happens, right, is now I've removed, right, my reaction's at equilibrium, right? I remove some products. Let's pretend I remove all the products, right? I got no products left, so my reaction is going to want to form products in order to reach equilibrium. Now you don't have to remove all the products, right? Just some of the products, and the reaction will go in the forward direction, right, to the right, and form more products. Okay. If I remove some reactants, right, the reaction in order to reach equilibrium has to form some of those reactants that you've just taken away, and so it's going to go to the left, right, and form some reactants, okay? So changing the concentrations, right, it's kind of straightforward, right? If I add something to reactants, it's going to want to get rid of some of what I've added, right? If I remove something, it's going to want to reform some of what I remove, right? So the chemical reaction, in order to reach equilibrium, is going to try to do the opposite of what you've done, right? You added something, it's going to remove some of that, right? You remove something, it's going to add some of it, right? And the only way a reaction can do that is by forming reactants or forming products, right? By having the reaction go in one direction versus the other, okay? Right, so an example of this, right, if I add O to the system, right, what's going to happen is my reaction is going to shift to the right, right, and I'm going to form, you know, NO2, right, and I'm going to use up some of that O2 that I added, right? If I remove NO, my reaction is going to shift to the left, okay? And it's going to consume, right, some NO2 to form NO and O2, right? Right, in order to undo what you just did by removing that NO. Okay. Now, in terms of temperature, okay, I find the best way to think of how temperature affects equilibrium and how it's related to the Chateliers principle is thinking about temperature as heat and heat as a reactant or a product. Okay, so in an endothermic reaction, that reaction takes in heat, takes in temperature in order to go. So heat here can be considered as a reactant. For an exothermic reaction, right, energy is given off, heat is given off, so heat is a product, right? And so if I increase temperature, okay, what that is doing is that's like increasing heat, okay, right? And if I increase heat for an endothermic reaction, I'm adding something to the reactant side, so it's going to form more products, right? And the reaction is going to go to the right, okay? Right? But if I increase the temperature, right, which is effectively like adding heat to an exothermic reaction where that heat is a product, then the reaction is going to go to the left and form more reactants, okay? Right? Similarly, right, if I decrease temperature, right, that's the same thing as decreasing my heat, okay? If I decrease temperature for an exothermic reaction, right, I remove some heat, right, I take some heat out, so my reaction is going to shift to the right in order to get some of that heat back, right? Just like it would for any other reactant or product, okay? So you can think of the effect of temperature as, you know, it affecting heat, and think of heat as a reactant or product, depending on if your reaction is endothermic or exothermic, and it works in the exact same way as changing concentrations. Okay. Right, an example of this is I have this equilibrium here, right, where the reactant side is pink, product side is blue, right? In this reaction, it is endothermic, so heat here is a reactant. So when I heat up my reaction, right, I increase the temperature, right? Arrow here, I'm increasing the temperature, okay? Right, my system is going to be even more blue, right? It's going to be this deep blue because I've added some reactant here, and that's going to shift my reaction to the right, right? To form products, okay? Now, if I cool this system, right? So in this case, I'm decreasing my temperature, right? That's going to remove some heat, right? This removes heat, right? When I remove that heat, right, my equilibrium shifts to the left. When it does so, it forms more reactants, which are pink color. My reaction now looks pink. Okay. All right. Now, I'm talking about volume and pressure changes. Okay. So this is most important with gases. Okay. So if I have a gas, right, and I decrease the volume or increase the pressure, right? Remember in our ideal gas law, right, PV equals nRT, right? As volume increases, pressure decreases, right? Right? As volume decreases, pressure increases, right? And so if I decrease the volume or increase the pressure, either one of those things, right, the reaction is going to shift to the side with fewer moles of gas, okay? And it's doing this because if you're, say, increasing the pressure, okay, or decreasing the volume, right, you have less space to work with, and your molecules are hitting each other more often because as pressure is increased and there's a lot less volume, right? So the reaction is going to want to form fewer gas molecules to alleviate some of that increase in pressure, okay? While if I increase the volume or decrease the pressure, the reaction is going to shift to the side with larger number of gas moles, okay? And that's in order, and it does that, right, to compensate for this decrease in pressure, right, this extra space that it has. Right, so kind of visually look at this, right? If I have 2A gas going to 1B, okay, and at some equilibrium, have some equilibrium mixture of A and B, okay? If I increase the pressure or decrease the volume, right, my reaction is going to form more B, okay, because there's fewer gas molecules on the product side of this reaction than there is on the reactants, right? There's 2 gases over here and 1 gas on the products, okay? So increasing the pressure favors the side with fewer gas molecules, which in this case has B, okay? While if I decrease the pressure and increase the volume, right, I now have a lot more A in my reaction vessel, okay? And that is because the equilibrium is going to want to favor the side that has more gas molecules on your reaction, okay? So because I have 2 gas molecules on the reactant side, this reaction goes to the left, forms more reactants, forms more A to compensate for this increased volume and decrease in pressure. Then finally, talking about catalysts, okay? As we talked about with chemical kinetics, right, catalysts increase the rate of a reaction, right, by finding some alternate pathway, right, lowering this activation barrier, okay? right? What that does is that makes your reaction faster, but that has zero impact on chemical equilibrium, okay? Adding a catalyst does not change the equilibrium mixture, okay? So a catalyst does not affect chemical equilibrium. It gets you there faster, but it doesn't affect the final equilibrium mixture, okay? And so that's it for chemical equilibrium. We're going to talk a lot more about equilibrium in future chapters, but that's it for this chapter, focusing on just the ideas and aspects of chemical equilibrium, the Chateliers principle, right? How we manipulate equilibrium constants with the manipulations of reactants and things of that nature.